The internet is burning, but maybe we have the solution. Have you ever stopped thinking about the sheer scale of data we generate every day? Every click, every scroll, every personalized feed. Where does all this data live in the greatest information age of all times? This map is not a secret. These are the data centers spread around the globe. They are many and huge. It is estimated that about 400 million terabytes of data are generated each day. It's mind-blowing. But is it sustainable? Let's get started. Hi, I'm Francesco, and I'm pursuing a PhD in Photonics in the Berlin-Brandenburg region, Germany. Science is my passion, and here my goal is to try making it more inclusive. Now, this is your smartphone, and it probably starts overheating after just a few minutes of gaming, especially in summer. Imagine what's happening inside massive data centers, where trillions of operations are running every second. Artificial intelligence systems run 24/7 on hundreds of thousands of GPUs, and if you think the energy and cooling requirements are astronomical, you're right. It's not surprising at all that Meta wants to build nuclear plants to power its computing systems. How do we manage this data explosion, which is only just getting started? The answer to this problem might lie in a revolutionary technology that's already reshaping the future. This massive environmental footprint is not just about the processing power. It's also about the cooling systems, the water usage, and the electronic waste. But there's a deeper issue here that you might not know. Today's computing systems are nearing their physical and technical limits. At the heart of this challenge lies a problem baked into the very fabric of modern electronics. A fundamental limitation in the way we connect components inside chips. The internet is burning, but the future is bright. And there is a promising solution. Its name is silicon photonics. Today we'll explore not only the limits of traditional electronics in terms of performance and energy efficiency, but also the revolutionary potential of silicon photonics and its exciting real-world applications. From photonic gyroscopes to biosensors that sound straight out of a science fiction. And by the end of this video, you'll see how light is leading us into the future of microintegration and why photonics could transform the way we compute, connect, and innovate. Data centers and AI systems are pushing the limits of traditional electronics. The networks are bound to become saturated, slow, and consume too much energy. What is the technological competition of the century? You know it. Elon Musk, Mark Zuckerberg, Sam Altman, scaling their systems by putting hundreds of thousands of GPUs to work in parallel. And this is just the beginning. Here is a surprising fact. These digital giants in the largest centers consume as much energy as 1 gigawatt, equivalent to the energy produced by almost 2 million photovoltaic panels, so solar cells, 100 million LED bulbs, or the Doc's DeLorean, which takes 1.21 gigawatt of energy to travel through time. Now check this out. This is one of only a few virtuous examples. We are in Covilhã, Portugal, where a data center has been built to use rainwater and wind for cooling, partially bypassing the issue. However, not all data centers operate this way, and slowing down technological development is obviously not considered as a solution. Some of the immediate benefits of increased computing power include more accurate weather forecasts, improved disaster prevention, and a better protein engineering. Think of this year's Nobel Prize for advancements in medicine, which can lead to more nutritious food and better drugs. Now let's examine the fundamental limitation to the performance of electronic technology, the current problem. In our computers and microchips, to charge and discharge transistors, a voltage difference must be applied to the wires that connect them. Electrons must be motivated to move and generate a wave traveling from one end of the line to the other. We are talking about incredibly complex grids of copper lines that in advanced chips, such as the one fabricated at TSMC, can stretch up to 100 kilometers in a space no larger than a droplet of water. These connections face a critical challenge that cannot be overcome: a limit known as the RC challenge, the resistance capacitance product. Every time you send a signal through a chip, it's like turning on a light bulb. The resistance and capacitance determine how quickly and effectively it happens. If the resistance capacitance product is high, it will take longer after flipping the switch for the light to turn on, in analogy for the transistor to electrically charge and transmit its state. And shrinking these connections for better performance creates a paradox. Higher resistance, more heat, and a greater energy loss. It's estimated that about 20% of this power is just lost in this jungle of metal traces. So how do we minimize this product? How can we transmit data faster? We need larger, shorter and more widely spaced wires to reduce resistance and capacitance. But you probably know Moore's law, which dictates that transistors are becoming smaller and closer together. And we are already down to a scale of just few nanometers. This bottleneck limits the speed and efficiency of our most advanced devices. Interconnections are the weak link of the chain. To overcome these limits, scientists are turning to silicon photonics, where data travels as light instead of electricity. Here is why it's revolutionary. Photons don't suffer from resistance or heat loss like electrons. And while electrical connections transmit one signal at a time, optical connections can carry multiple signals simultaneously, thanks to a technique known as multiplexing. Light, when propagating, essentially maintains its identity, even when encountering other light. And although localized interference phenomena can occur, different colors can travel at different speeds along the same line, each of them carrying unique information. And this means that a single optical waveguide can handle more data with less energy. Currently, there are systems based on fiber optics and optoelectronic transceivers, which are devices that are plugged in the servers and convert signals from the light domain to the electric domain, are already used for data transmission via fiber optics. The real breakthrough lies in bringing photonics directly inside the chip. Imagine light traveling through nanostructures, delivering terabits of data per second with unprecedented efficiency. In a brilliant paper from Stanford University, researchers combined a series of highly sophisticated design and fabrication techniques to transmit 1.12 terabit per second over a single nano waveguide. At this speed, you could download 50 gigabytes of data in just 3.5 seconds. In these videos, I'm trying to make science more inclusive. If you are enjoying watching it, please consider to subscribe and spread the word. Let's make science more inclusive together. And let me know in the comments if you want to know more about a certain topic. Now let's get back to the juice. Let me share with you another truly futuristic example: photonic gyroscopes. A gyroscope is an instrument that measures and maintains orientation and rotation. Electronic gyroscopes already exist and are widely used in mobile devices, drones, video game controllers, cars, airplanes, and other systems which require precise, real-time orientation measurements. These are generally micro-electromechanical systems. Inside, there is a microscopic structure that vibrates at very high frequencies. This structure is suspended and can vibrate in specific directions. When the gyroscope moves or rotates, the coriolis force acting on the vibrating structure causes a lateral displacement proportional to the angular velocity. The lateral movement of the vibrating structure is measured using capacitive or piezoelectric sensors, which convert these small variations into electrical signals. As you might guess, they are crucial for autonomous and inertial navigation systems. It means when there is no GPS signal. Now imagine replacing all these moving, relatively fragile parts with fixed structures that carry light. Let's see how they work. They leverage the Sagnac effect, which is itself astonishing. When a beam of light is split into two parts traveling in opposite directions around a circular path on a rotating platform, the two beams of light take different times to complete the path, due to the platform's rotation. As a result, when the beam recombine, an interference pattern emerges, highlighting this temporal asymmetry and allowing the measurement of the rotation which caused it. Now, these gyroscopes offer longer lifespans in comparison to the electronic ones, extended from 10 to 20 years, resistance to temperature changes, shocks and vibrations, and greater accuracy. You are probably already thinking, These gyroscopes are perfect for space exploration. But there is an additional reason why this is true. Can you guess it? Yes, it's their resistance to ionizing radiation. It's called radiation hardening, and this is already a challenge. It involves making devices resistant to malfunctions or damage caused by radiation, such as cosmic rays or nuclear environments. So imagine, the application can be in space, in nuclear plants near reactors, and particle accelerators, such as the CERN in Geneva. A fundamental element here is the so-called passivation, which is typical of silicon photonics, and it's the deposition of a silicon oxide layer over the underlying devices. Simply put, it acts as a protection. The controlled deposition of silicon dioxide, which is essentially quartz, was an absolute revolution for the entire electronics industry. But we'll discuss it in another video. If you don't want to miss it, consider to subscribe. But now let's keep talking about microchips. And we have already understood that it isn't just about performing billions of calculations per second, like in computer and smartphones. But there are other functions that can be integrated in silicon and other materials at the micrometric and nanometric scale. We have just seen rotation sensors like gyroscopes. Let's look now at perhaps the most remarkable example after telecommunication: medicine. Silicon photonics is revolutionizing medical diagnostics. This can be done by integrating microfluidic channels, nanophotonic waveguides and electrical connections on the same chip, and building a so-called lab on a chip that can analyze proteins, antibodies and even gases with high precision. For instance, the surface of certain nano waveguides can be functionalized to change their chemistry, so that when a specific protein, like an antibody, binds to it, it causes a change in the optical signal that can be measured. It's like two pieces of a puzzle that connect when they match and therefore stick to the surface of this waveguide. This way we know it's there. Despite its promise, silicon photonics still faces big challenges. In particular, the integration of a light source like a laser directly on a silicon chip, made of the same material as the substrate, the chip itself. But researchers are closing the gap, paving the way for devices that will reshape the world, and industries from AI to medicine. Remember, the future is bright. In the next video, we'll talk about how existing optical fiber networks can support early earthquake detection and help saving lives. Consider subscribing if you want to know when it's out. It's free. It's just a click and it lets me know that you are also appreciating the work that I'm doing here. I hope you enjoyed this video. Thanks for watching. Spread the word and let's make science more inclusive together. See you on the next one. Ciao.